In this video lecture, we want to spend a little time exploring time dilation and length contraction, which we introduced last week. And so here's the idea. We're going to do a little star tour here. Imagine a trip to a star 5 light years away. Okay, so if we could go there at the speed of light, it would take presumably 5 years to get there in a certain frame of reference, as we'll see here. So for our trip, we're going to assume that our velocity, so here's Earth, here's the star, sort of compressed together there, but the idea is that's 5 light years away. Here's, maybe it's Bob's spaceship, and traveling at velocity v, and we're going to assume v is 0.943 times the speed of light. The reason we chose that, it gives us a gamma factor of 3, so a nice even gamma factor there, Lorentz factor. So here's what we want to do, is we want to analyze the situation first from the perspective of an Earth observer watching Bob, so maybe Alice is on Earth, watching Bob travel to the star, and then analyze it from the rocket observer's perspective, frame of reference. That would be Bob in this case. So let's just think about this from somebody watching on Earth, watches Bob go by at velocity v, presumably he's had a lot of time to get up to speed here, so he's going nice constant velocity when he goes by. We also set up here, so again, imagine for the Earth frame of reference, it's really the Earth star frame of reference because they are stationary with respect to each other. So once again, we have to imagine a lattice of clocks going all along in the Earth star direction here, and all those would be synchronized in the Earth frame. And so the idea here is that when Bob goes by Earth, we'll set it up such that the Earth clock, the clock on Earth, is time t equals 0, and Bob's clock that's going along with him is also time t equals 0 at that instant as he goes by. And all the Earth clocks are synchronized in the Earth star frame of reference, and Bob, too, has his imaginary lattice of clocks extending in both directions to infinity, and all those clocks are synchronized in his frame of reference, which, of course, in his frame of reference, he's not moving. He's stationary. And it's really the Earth and star system that is moving. And we'll get to that in a minute. But let's look at the Earth observer first and just measure, how long does it take at 0.943c, gamma factor 3, to get for Bob to get from the Earth to the star. So we have travel time here is simply going to be 5 light years, 5 Ly, for light years, that's the distance from the Earth to the star, divided by the speed, which is 0.943c, 0.943 times the speed of light. And as we talked about in a previous video clip here, nice thing about using distances like light years or even light months, light seconds, although typically we use light years, especially for astronomical distances, is that the speed of light is simply 1 light year per year, almost by definition. The definition is the definition of a light year is the distance light travels in 1 year, technically in a vacuum, which of course outer space isn't quite a perfect vacuum, but pretty close to it. And so we get 1 light year per year for c. So essentially we're just doing 5 divided by 0.943 as long as we're using units of years. If we were using units of light months here, then the answer would be, we'd have 1 light month per month for c, and the answer would be in months, and so on and so forth. So as long as we keep track, hey, we're using light years here, the answer of 5 divided by 0.943 is going to be the number of years, travel time, to get there. And if you do that, it comes out to be 5.30 years. Okay, and it's always good to check, does that make sense? Well, 5 light years, and it takes, you're not going quite at the speed of light, just a little less than the speed of light, so you would assume it takes a little longer than 5 years to get there, and of course that's the answer we get, 5.3. So that checks out in terms of how we think about that. Now, another thing we want to do here from the Earth observer's perspective, so that's the first thing. Second thing we want to do is, as Bob goes by here, as our rocket ship goes by, takes a photo right at that instant on the Earth star lattice of clocks. Takes a photo both of the Earth clock there and Bob's clock. They both read t equals 0. And then when Bob, the rocket, gets to the star, 5.3 years later, take another photo. And so in that photo, the star clock will read 5.3 years because this is from the Earth observer's perspective. And Bob's going along at 0.943 C. And when he gets there, 5.3 years have elapsed on the Earth-star system of clocks. And so the question then is, really, what does that photo show? We know the photo shows 5.3 years for the star clock. What does it show on Bob's clock as far as the Earth observer is concerned here? Well, this is where we think, okay, Bob's clock is a moving clock with respect to the Earth-star system. Time dilation factor is what enters in here. So in terms of what the Earth observer sees, say Alice sees as Bob goes by, is Bob's clock runs slow compared to the Earth-star system of clocks. How does it run slow? It runs slow by a factor of gamma. Remember, our basic equation is, we'll say, we've written it in different ways in terms of Alice versus Bob, moving versus rest frame. Here maybe we'll do rocket and lab frame, where the lab frame is the Earth-star system. Or actually, let's just call it the Earth frame. So delta T for the rocket here is 1 over gamma. The elapsed time on the rocket is going to be 1 over gamma times the elapsed time in the Earth star frame. Okay? And gamma is 3. We've set that up. So if delta T on Earth is 5.3, then the Earth observer sees, let's not use C, we try to avoid that, although we use it sometimes, observes, in this case, observes means photographs, so I might as well say observes / photographs. Rocket clock at the star, and the time on that clock is going to be the elapsed time on the Earth clock, 5.3 years, divided by 3, divided by gamma. And so that's going to be equals 5.3 years over gamma, which of course is 3 here. And if you do 5.3 divided by 3, you get 1.77 years. Of course, I've worked out the numbers beforehand, so I can't do that in my head just automatically, but just remember the numbers we're using here. So that's, in other words, when Bob gets here in his rocket ship and the photograph is taken, the star clock, which belongs to the Earth-star last system, will read 5.3 years. The rocket clock will read 1.77 years. And then you're going, now, hold on a minute, wait a minute here. How can that be? Because Bob is going at 0.943 C, about 0.9 times the speed of light. It's 5 light years to get there. How can it only take 1.77 years for him to travel that distance? Clearly, he would have to be going faster than the speed of light, or it seemed so. And here's where we have to remember the different frames of reference and different perspectives. So now let's take a look at what the rocket observer says, what Bob, in this case, not says, but would see, would observe as it goes along here. So from the rocket perspective, and by the way, you may have noticed this already, this is very similar to our muon problem. In fact, really an exact analog, just another version of the muon problem. The muon problem is a version of this, although we're going to take this a little bit farther than we did with the muon problem. So having that hint, then, think a minute, what does Bob, the rocket observer, see as he's traveling along in his frame of reference? And actually, that's a misnomer. He's not traveling along in his frame of reference. He's stationary in his frame of reference, and it's the Earth-star system that's moving with respect to him. The star is rushing towards him. And therefore, here's where another aspect comes in. That's not time dilation. It's length contraction for him. He observes, let me just back up. Clearly, when he gets here at the star and the photo is taken 1.77 years on his clock, he has to agree with that. He agrees, yes, absolutely, I can see the photograph there. Clearly it says 1.77 years. Clearly I can see in the Earth observer, in the Earth frame of reference, the clock for the star is 5.3 years. And to understand that discrepancy completely, it'll take a little while here, but for the moment, there's no disagreement about the photograph here. It's not like the number is wrong. This is what's on Bob's clock. This is what's on the star clock, the Earth star system clock at that point. So now we're going to switch from the Earth frame of reference to Bob's frame of reference and say, okay, what is he observing here? And so, again, the idea is he's stationary. It's the star that's rushing towards him. And so this distance here, essentially between the Earth and star, is contracted for him because that distance is moving toward him. Imagine if you had a rod there or something, you could connect the two, right? It moves that way. That length of that rod, or just the distance, length of the distance here between the Earth and star, that's going to be contracted to Bob because that's a moving frame of reference at really negative v going in that direction to him. And so what is that distance? So the rocket observer observes that the Earth-star distance is contracted. It's less than it is in its proper frame of reference, in its regular frame of reference. In other words, the proper length is shorter when it's moving. And so the proper length here in the Earth-star frame of reference between the Earth and star is not 5.3, it's 5 light years. Where do we put it? Here, up here. 5 light years. Okay? To Bob, however, the rocket observer, it's 5 light years divided by gamma. Because, again, in the moving frame here, and let's not get confused here with rocket and Earth. So I'm going to use moving and rest frame because you can switch back and forth between the frames. And in this case, for Bob, he's in the rest frame. It's the Earth-star system that is moving. So the length in a moving frame is 1 over gamma times the length in the rest frame when it's at rest. And so when it's at rest, it's 5 light years. But Bob sees it moving at a velocity v, 0.943 c. And therefore, if he measures that distance, he's going to get 1 over gamma times 5 light years. And gamma, we've chosen to be 3. And so he sees, we'll call it d, the distance between the Earth and star. So we'll say DES, the distance between the Earth and star. It's not a very good D there. Sort of like a lopsided 0 or something. There we go, a little better D. Distance between Earth and star according to, this is in the rocket frame now, the distance between the Earth and star in the Earth-star frame is just 5 light years. In the rocket frame, it is 5 light years divided by gamma, which is 3. And when you do 5 divided by 3, you get 1.67. Equals 1.67 light years. Okay? So to Bob, the rocket observer, he sees that distance as 1.67 light years. Okay? And now let's see, okay, so he's saying 1.67 light years. He's saying, I see the star rushing toward me at 0.943 c. And by the way, a question that I think has come up in the discussion forums, and a very excellent question, actually, that we never quite addressed directly is, what if velocity changes? It seems length changes, time changes. Does velocity change between frames as well? Do we have to worry about that? We'll actually be talking about that a little later this week. So we will see that the short answer is no. The velocity is the relative velocity between frames of reference, and it's going to be the same for Bob in this case, and the same for Alice, say, in the Earth-star system, the relative velocity between them. We'll see cases, though, where if we'll do an example where Bob, say, has an escape pod, and he shoots off the escape pod from his spaceship at a certain velocity, then what velocity does Alice see that as? So we'll do examples like that. But back to our situation here, just to indicate, yes, v is going to be the same for either one of them. Bob, Alice sees Bob traveling along at v that direction. Bob sees the star moving toward him at 0.943 c as well. So from Bob's perspective then, from his frame of reference, he sees the distance that the star has to travel to get to him as 1.67 light years, because it's contracted by the factor of gamma. And how long does the star travel toward him until it reaches him? Well, it's the time on his clock, 1.77 years. We know that the star and Bob, the rocket, are in the same place when Bob's clock reads 1.77 years. And so what does that mean here? Does this connect with that? So let's think about this a minute. Distance the star has to travel to get to Bob, according to Bob, is 1.67 light years. It's traveling at 0.943 c to him. So let's do that calculation. Let's just say that time for star to reach Bob, we'll say. So Bob is in the rocket. Time for the star to reach Bob is simply the distance divided by the speed, equals 1.67 light years. 1.67 light years divided by 0.943 c. That's how fast the star is moving toward Bob and his rocket. And again, we're doing c is 1 light year per year. So 1.67 divided by 0.943, the answer is going to be in light years. Do you know what you get? If you do it, you get 1.77 years. In other words, it's all consistent. Okay? So that from Bob's perspective, he sees the star rushing toward him at 0.943 c. He sees the distance the star has to travel as 1.67 light years. And he sees his clock tick for 1.77 years when the star reaches him. And the photo is taken at that point, and his clock says 1.77 years. Meanwhile, of course, from Alice's perspective on Earth, she sees Bob traveling toward the star at 0.943 c. In her frame of reference, that distance is 5 light years. Therefore, it takes Bob 5.3 years. So when he gets to the star on the Earth star clocks, Alice's lattice of clocks there, it'll read 5.3 years. And Alice observes Bob's clock, though, running slow by the time dilation factor, and therefore observes Bob's clock to be 1.77 years. Okay? So in that sense, Alice says, it makes sense to me. This certainly makes sense to Alice. And she says, Bob, your clock is running slow. I don't know what the problem is over there, but I get it as 1.77 years. Meanwhile, Bob says, well, I don't know about this 5 light year distance you've measured, because to me it's clearly 1.67 light years when I measure that distance. But you are right, it takes me, because it's a shorter distance in my perspective. Obviously your measuring system is messed up, it looks like. But for 1.67 light years, at the speed the star is coming toward me, 0.943 c, it takes me 1.77 years. And therefore, at least they both agree that the 1.77 years is correct, although for different reasons there. Because Alice is saying, hey, your clock is running too slowly. And Bob is saying, no, it's not my clock that's running too slowly. It's your distance measurement that is messed up. But they both agree on the 1.77 years. It's a little more difficult, though, and this is what we're going to be heading toward this week to a certain extent, to explain how does Bob explain this 5.3 years factor here. So that's something we're going to have to do. But there's another thing here, too. We say, okay, sort of see how it hangs together. There seem to be some loose ends we're going to have to worry about. It's one of those things you have to just ponder as well and let it sink in for a while. And sometimes it just takes a while. I've been in classes before where it didn't really sink in until after the class was done, unfortunately. But sometimes that's the way it is. But let's think about something here. Okay, let's go back to Bob's frame of reference, and he's observing Alice's lattice of clocks, the Earth star lattice of clocks. You can imagine a whole bunch of them there, all synchronized for Alice. But as Bob is observing that lattice of clocks go by, let's think about this a minute. Doesn't time dilation work in that direction as well? And the answer is yes. Works both ways. And so if Bob is seeing the elapsed time for the star to get to him is 1.77 years, how much elapsed time does he see pass on the Earth star clocks? Well, time dilation applies. It's the exact same relationship applies here, except let's make it a little more general here from what we had before. So it's delta t moving. Okay? In other words, I'm observing a clock in a moving frame of reference. Okay? And this is rest. So if I'm at rest, I'm observing my clock in my frame of reference, and then I observe a moving clock. That moving clock is going to run slow by the factor of gamma. So Bob, in his frame of reference, has his clock there in the cockpit with him. He's observing Alice's clocks rush by him in the Earth-star system as the star comes towards him. Therefore, he will see those clocks running slowly by a factor of gamma. And so when he sees on his clocks ticking away nicely, 1.77 years, how much elapsed time will he see on Alice's clocks? And the answer is, we're going to have room over there, so we'll squeeze it in right here, say. Okay? So this is Bob's observation. Sorry, squeeze that in there. So that's observation of, we'll say Alice's. Okay, just remember Alice here. So here's Alice. Get her up here. Here's Bob. B for Bob. Bob's observation of Alice's elapsed time. Okay, according to her clocks. It's going to be 1.77 years, because he's got his clock right there. It's ticking away nicely. When the star reaches him, yes, it's at they take the photograph. It's at 1.77 years. Her clock's at 5.3 years, but we're not going to worry about that for the moment. She thinks it's correct. He has other ideas about that. But what is the elapsed time from Earth to the star, or really the star getting to Bob here, that Bob sees on Alice's clocks? And it's 1.77, because that's the time on his clock. So it's 1.77 years divided by the gamma factor. It's always 1 over gamma here in this case, when we're going in that direction. So that's divided by gamma, which is 3. And the answer you get if you do that is, I think, 0.59 years. And now you really go, huh? Right? How can this make sense? You know, we can sort of see, yeah, okay, I get time dilation. Alice will observe Bob's clock's running more slowly, and so instead of 5.3 years, gets 1.77 years. And sort of get Bob over here, the rock observer, the distance is contracted, right? And therefore, shorter distance, and therefore his clock will run for 1.77 years, okay? But then Bob, looking at Alice's clocks running slowly, just as Alice sees Bob's clocks running slowly, Bob is seeing Alice's clocks running slowly. By the factor of gamma, you get his elapsed time divided by gamma is 0.59 years. How in the world does, you've got 5.3 years. Isn't that the elapsed time on Alice's clocks? That's the elapsed time she's getting. How is Bob getting a value of 0.59 years for the elapsed time on Alice's clocks? And to understand this quantitatively, we're going to have to do some work this week. We're going to develop something called the Lorentz transformation, because that's going to help us understand this. Among many other things, it's useful for much more than just that. So it's going to help us understand this. But I'll give you a hint on it. And that is, when you're thinking about the special theory of relativity, you can't just focus on time dilation. As we've seen here, time dilation and length contraction go together in the analysis. Often from different frames of reference. In one case, you're using time dilation. From the other perspective, it's length contraction that is the issue. But there's a third thing here, too, that we cannot forget. And that is the relativity of simultaneity. That clocks synchronized in one system, frame of reference, are not synchronized in the other frame of reference, moving at a velocity via an inertial frame of reference. And that is the key to understanding this. And earlier on in the course, qualitatively, we talked about how leading clocks lag. That if you have two clocks, say, or a series of clocks moving past you, at obviously for this to really be observed, it has to be a pretty high velocity, but in principle, it's for any velocity. As it's moving past you, if you're observing those clocks go by, the clock in front is going to lag the clock behind. The clock behind will be ahead of, time-wise, the clock in front. And that is the key to understanding this discrepancy here. And we want to be able to understand it quantitatively. We want to be able to show that add the numbers together in some way, and yes, you actually do get the 5.3 years back in. So to do that, we have some work to do this week, but this is, again, exploring time dilation and length contraction. Originally, I thought I would do this in a couple weeks when we talked about like the twin paradox, but I decided it was good to introduce it this week to try to mull over a little bit how time dilation and length contraction works, and also the relativity of simultaneity. So that's where we're heading over the next few video lectures, to do the Lorentz contraction and then do leading clock's lag in a quantitative sense, as well as looking at some aspects of velocity and so on and so forth.